Everybody. So this time we're gonna go and continue our practice session from last week. Again, I apologize for not being available. I had an urgent thing that I had to attend. It's by the way, it's a really interesting demo that we showed in Ignite, and I hope that by the end of this course I will be able to show it to you, and it's gonna mean something to you. So today we're gonna talk about basic Unix programming, and this is basically the goal is to find some similarities from the micro level of the operating system that we all know or going to learn, and how we extrapolate it into the cloud, into a cloud environment. So when we take the Unix operating system as the example, it's all about a core component of understanding basic system programming. It handles file descriptors. So basically all peripheral devices, even keyboard and screen, are files, are shown and managed as files in the file system. Even the shell command that you are writing to is considered as a file, okay? And every file has a file descriptor. And it's a very, very important concept to understand for understanding the much more complex concepts that we're going to discuss during the course. One of the interesting thing is that it's file descriptors is a single homogeneous interface to handle all communication between the program and the devices. So, for example, when we want to do something, for example, when we want to write to a file, we need to open the file, check the writes, do something like write or read, and then return the program to the program the file descriptor, and then basically the communication is done through the file descriptor. And the same thing, the same pattern follows when you are doing similar things with networking. When you want to send something to somebody, again, you're gonna pick up. We're gonna see that we are going to identify and allocate a file descriptor that indicates on the socket, the network socket, and whenever we want to write something to somebody, we're gonna write it to the socket, and then from there it will end up to at the place that we wanted to send. Let me just make sure that nobody is interrupting me here, and I'm gonna shut this thing off so we can talk a little bit more. Okay, so yeah, so when we try, and now and let's look how does it and let's see how does it look. So every communication to the file descriptor done through system calls, okay? And this is and basically understanding that the concept of system calls is also super important, because if you're not familiar with this concept, I suggest that you go and read a little bit about it. But essentially, a user does not interact directly with the system. Okay, and of course there are many good reasons for that. One of it will be a security one. We don't want that every user will have the ability to mess up with the system. So therefore there is a layer of system calls that masking user calls and translated into system calls. So it's more cohesive and secure. And also there are libraries. So libraries can be usually are using system calls to interact and to fulfill and to fulfill the user needs. Usually libraries are written on system calls based on specific scenarios. So for example, if you will install Apache web server, the communication of the Apache code will execute Apache libraries that will eventually execute the system calls. Of course, that the user always have the freedom to call the system calls directly. But essentially, there are two layers that where system call masks all these things, and as it runs on different level of permissions. For file, as far as file descriptors is concerned, system calls handles mainly four system calls, and those are self-explanatory: read, write, open, and create, and LSIC. So, and for those who think that I miswrite create, it's on purpose. I think that the author of these system calls wanted to keep the system calls length to 5, so this is why he omitted the e in the create. But essentially, read, write, open, and create is what we can do with files. LSIC is a little bit more interesting. Is a way to provide offset to a specific file, so you ended up you can have a random access to the file. Yeah, so this is again what we see here is an example, and we're gonna see it very soon in real life. We have a program that basically accept all kinds of arguments, and then essentially open a file for reading and writing it. And this is again a very primitive way to implement the copy command, the CP command in Linux. So if we can go through this thing really quick, we have the program will get three arguments, and if there will not be 3 arguments, we're gonna say the copy cannot be done, or basically we're gonna say that copy we need to have some sets of information, and then if the argument C, the length of argv is 3, we assume that argument 1 will be for the destination file, the source file, and argv2 will be the destination file. And then once that we passed this part and we didn't exit so far, we're gonna go through a while loop, and we're gonna iterate through the lines in F1, which is the argv1, and then for every iteration we're gonna read a chunk in the size of buffer size that we specified here. And then essentially once that we have it in the buffer size, we are going to, in the buffer here, we are going to write this thing into F2. And basically this is the copy. This is how primitive copy happens. And as you see, the system call that we are discussing right now is read. Okay, and as long as read returns a value that is greater than 0, it means that it was successful. And this is a standard in Unix system calls. Whenever the response to the system calls is a -1 or not greater than 0, it indicates an error. So basically this while will run as long as it is valid. And one of the reasons that it cannot be valid is that a file was deleted, or a file is the end of file was reached, and then therefore the buffer cannot be populated anymore. And as for the write system calls, as we see here, the same thing goes as well. But here, the write response is the number of bytes that was written into the file, and if we write n bytes and we get response that is different than n, it indicates an error as well, and this is where we write to the standard error. And by the way, just to make things more complicated, standard error, which is stdr, it's the standard error, it's also a file, and I think that it has a well-known file descriptor. I'm not sure but whether it's 2 or 1. I think it's 2. So basically, if we would write this program with stdr with the number 2, it will do the same thing. And all these constants and declarations are written here in those 3 includes. This is again a very basic program. So let's just see how does it work. So what I have here a Unix system. Okay, it's Ubuntu. I don't know what Ubuntu is, but doesn't matter. So I went to our course repository, Unix sys programming. I clicked on this thing, I copy it, and then I typed git clone, and then I paste the copied URL, and now I have it here. So okay, so let's see. We are talking about this command argv and argc. Let's open it. So vi. This is a simpler one. Copy. Okay, so this is our command. Okay, and what I wanted to do here is that to basically compile it and see if it's what kind of things we can learn about it and how it is related to the overall course of our all topic. So first of all, I need to compile it. So I'm gonna do gcc copy -o, copy -o, ls -ltra. We have a copy -o, and then let's just copy this file. Let's see what we have here. Let's see what we have here above, so we can use this one. Okay, so we have this file. Let's see what is the size of this file so we can see if it makes sense. Sorry. It's 1.5 megabyte. That's good. That's good. So let's copy it. So we're gonna do copy, Redis, tar, and let's copy it to here. What? Oh, that's good. We got an error. I didn't anticipate it. So it says write error on file. Oh, now I know what is the problem. So before I am trying to speculate what is the problem, let me try to do this thing and write test. Okay, so the reason that this thing failed, it's because that the file is compressed. So this program, that's kind of interesting, that this program cannot be supported because it cannot read and cannot copy the file as it is, because it's already compressed. And when you apply compressions to the file, it is, I think that the operating system will not allow you to read this thing. But let's see if we can do something about it. let's see, because again, when we see that write error on file, this error happens here, okay? I cannot copy write error on file. So which means that when we tried to read and to copy the lines, it didn't succeed probably because of the compression. So let's see if we have an issue of permissions. So as we can see here, a user can read write, a group can read write, and everybody can read. So, and we are the owner, so we don't have a problem to do read and write, okay? So it's not a permission problem. So I guess that it's because that it's compressed. So what can we do is that, you know what, let's just copy this Redis. This .gzip. We're gonna copy it to here. Okay, so now we're gonna have it here, and I'm gonna simply copy, unzip it. Okay, and unzip is done by guzip, because if you want to zip it, you do gzip, and gu and zip is. Now I have it open, and I'm very interested, and you can see, I'm very interested to see if we can work on this file. I will argue that we still cannot, but let's try. That worked. That worked because, so if we cd, so if we look at ls test, okay, ls-l test, we can see that it's a file, and now we know that it's a tar file, so we can open it like that. So we can do tar minus x vf. Let's do use the verbose and open it. X is for extract test. Cool. So let's do lstr-a, and we see that this file was opened here. I just want to find it. Okay, see, it's here. cd. This is the file. So what we learn from here is that this program was able to read and write as long as that it could write the files, but I guess that it could not do it because the file was compressed and could not be understood by the right system call probably did not understand and read it correctly. Another interesting thing that I wanted to call out here is that permission and return code is definitely an important thing, but also if we can see here the buffer size, and I think that this is strongly related to a comments that we saw in one of the students' calls about what will be faster to copy, because essentially if we have a big file, and do you know how to generate a big file? Let's see. We can, by the way, if you don't know how to generate, and I don't remember how to generate a big file, you can always do how to generate a file with dd. Okay, and creating a large sign in less time. Yeah, this is so, and this is the command. I always don't remember on top of my head. So basically, if I want to create a file, just a big file, I can use the dev u random. By the way, dev u random is always, I have here. Okay, dev u random is will generate, the output file will be in the size of 10 gigabyte, and I think we don't want to go to 10 gigabyte. Let's do 100 megabyte. Okay, and we want to take a chunk. The buffer size will be 10 megabyte. Okay, let's see. Yeah, this is the command. So dd, let's see, so it's this of, this is the, so we want to call it big file. We're gonna call it big file. We're gonna just use it image, just and then count equal to 1. I wanted to specify this is yeah, and the buffer size is equal to 10 megabyte. So what do you think will be the size of this file? Let's see. du minus sh is the big, and you can see it's 10 megabyte. Because what he did, it basically wrote something from the urandom one time, a buffer size of 10 megabytes. So if I'm gonna, and you're probably gonna follow, if I'm gonna write 100, what will be the size of the file? Basically, it's 100 times 10 megabyte. As you can see, it's going a little bit slower. And actually what we see here, this is exactly the point that I'm trying to convey, but instead of dd, we'd copy. So basically, if we wanted to do the same thing in our program, we always have to be conscious about the buffer size. And I guess that the question here is that what is the buffer size impact on the speed of the execution? So if we have a large buffer size, we're going to read from the files, we're going to have less iterations, right? Because we all the time read big chunks and write. So since read and write are the expensive operations, I'm going to stop this thing. Since read and write are the expensive operations, they are going to take the most time. So therefore, we want to execute as less as possible read and write operations. So therefore, we're going to use a big chunks of buffer size. So let's see if what I have here. Let's see what is the size that was. Okay, so you see, so as I said, we have 110 megabytes. So essentially it was supposed to write a size of 1 gigabyte, okay? And I stopped it when it reached almost the 1 gigabyte, which is 811 megabyte. But that's okay. So now let's try and copy this file, okay? And this is, I guess, the thing. So if I am doing time and doing copy, operate big data, you know what? Yeah, and then I wanted to use a different size. Let's write 10, okay? Because I think it's gonna take some time and it doesn't convey the point. So the size of this thing will be 100 megabyte, okay? 100 megabyte, and we can see du minus sh big. Okay, so it's 100 megabyte, that's good. So now if I wanted to copy the big into test.image, okay, we're gonna see how long it takes. It took this much, okay? This was pretty easy, but so let's do 50. I want a little bit bigger because I want you to feel the difference here. So what I'm doing right now, I'm creating a bigger file. Have something to drink while we are waiting. Excuse me. So what we are doing here is that we are now creating a bigger file, and hopefully when we're going to copy it, we're going to see here a much more substantial numbers, you know, like a little bit larger numbers, so we can exemplify what we do here. So du minus sh of the big file is 500 megabyte. That's good. So now let's do the same thing. We're going to copy. The time is just indicating that the shell will write this thing, will capture the execution time for us. So basically we want to copy the program that we have here and see how long it takes. Now we obviously see that it takes much more time than copying than the previous execution that we copied here, that took us less than. Okay, so now we have 26 seconds. Okay, so now if we wanted to, so let's just take this thing and keep it here, take a note of it. Okay, and now let's do something, hopefully improving it. Okay, so the buffer size is 8192. So we can do now, let's say, so we have a 1892. Who knows how much megabytes, how much bytes it is? I don't know if you know it, but you divide it by 1024. So the buffer size that we have now is 8 megabytes. So it reads 8 megabytes every time. So now let's read 16 megabytes. So 16 megabytes times gonna be this one. So we're gonna do this one. So now we're gonna double the amount of buffer size, and hopefully by 2, and I hope that by now you all understand that once you increase the buffer size by 2, you decrease the number of read and writes by 2 because you read more. Okay, now we're gonna compile it. -o copy.o. Okay, and yeah, this is just warning. And now let's execute this thing again, and hopefully this will be less than 26 seconds. It's the same. Oh, but the problem is that we have segmentation fault, which is a problem. It means that the program exited in crashed essentially. So oh, maybe we don't have enough cut proc mem info. Oh, I see. We don't have so much memory. I see. So what we are going to do, let's try to do something else. Let's use 4K. So instead of increasing it, let's decrease it and see what happens. Let's do 1 megabyte. Let's see if that will work. So now this execution is for 1 megabyte buffer size. 1 megabyte buffer size. Let's take time and see how long it takes, and then we're going to take 2. Okay, so here we got 17 seconds, okay? And this is 48 buffer size. Let's see how long it's going to take us here. VI copy. So 2048. Let's compile it and let's execute it again. See how it's done, if it's done better. And then we're going to draw some conclusions. Same thing, 17 seconds. Okay, and now let's increase it to, let's have it to 4, 0. So we're gonna have 4 megabyte. Let's see, we're gonna compile it, gonna execute it. 496 buffer size. "17 seconds," the same thing. And when we go with our original operation, or original execution, we got 26. Okay, so I'm not gonna write this thing. Okay, so for 8 megabyte, we got 26 seconds, and for 16 megabyte, it crashed. Okay, so how about we try here 512 just to see if it's consistent with our results. VI copy, and I will tell you why it is giving you this weird results in a second. Okay, this is 18 seconds. That's probably okay. So one. Okay, so what do we see here basically? We see here the impact of and so you see it's 17 and 18, it's the same thing. So what we see here is the impact of the buffer size on the response time of the program and how long it takes the program to do. Now the reason that the more one will say, and I would argue that the more memory you are going to use, the faster your application will work. However, since our application is probably our resource, our VM is not has a lack of memory, and maybe the memory, so which means that we don't have so much memory. It might, so what will happen basically is that instead of writing to the memory when the copy is working, when the user is reading to the buffer size instead of reading to the memory, and since he doesn't have enough memory space, he reads the buffer size, writes to the disk, and then read again, and then write again from the disk, and therefore it takes more time. So sometimes when you use a huge buffer size, the operating system does swapping. And swapping means that you, instead of read and write through the RAM, the memory, which is supposed to be fast, it goes through the disk. Okay? And I guess that when I'm going to ask you, hey, what will be the optimal buffer size? How you can size your system? You can take those numbers, okay, and plot it. Okay, so you're gonna have the size here and the time here, or the time here, or the size here, and you can see that it is going like that. And then you're gonna find the optimum points based on the size of your system, which is the mem total. As you can see, the total memory that you have here is 3 gigabyte. Yeah, it's 3 gigabyte, and also you can do the same thing for the CPU. You can see here that you have only one CPU here, and this is its size, okay? And this is the cache size and all kinds of details. So this is an example of how you play with all kinds of configurations that will impact the operating system performance. Now I want to address a question that was given by somebody about question number 3. So let's say you are about to design a cloud computing service that requires an execution time of not more than 300 milliseconds, and the workload will create an average of 100 global access per operation. How many nodes are required if every node has the following spec? Okay. I think that I discussed this thing right now. Let's see. So a quick guidance to how you determine how you handle these things. So we need to, it requires an execution time of not more than 330 milliseconds, right? So every command that we execute, as we executed here, okay, supposed to be not more than 330 milliseconds. So the number here, once you execute your command, it shouldn't pass more than 330 seconds. This is an important thing. Think about the example for this kind of use case is that 330 milliseconds is a famous KPI, because most of the requests that you send to Google or to Facebook, they were supposed to send the online request supposed to return with this 90% of this call supposed to return with this time frame. So this is why I came with this. Now you need to understand what do you need to have, what is the spec that you need, how many nodes you need in order to provide this kind of SLA, given this amount of hardware that you can have. Okay, so for example, so in this example you get one socket, so it means that you have one CPU that can do 2.66 gigahertz, okay, operations. So if I will give you a hint here, you need to convert this number into time, okay? Converting frequency to time, I will let you go and do it yourself. It's pretty simple. And then you have 100 global accesses. It's basically, you have all the information, you just need to multiply them, okay? So again, think about what you need to achieve. You want to return response time of 330 milliseconds, okay? You need to do an average of 100 global access per operation, okay? And you have the list of one machine, of how much one machine can give you, okay? And one machine can give you, and it's written here. Oops, it is written in this number, okay? So try to think again, and I hope that you will get it, and if not, we're gonna go through it in the next session. Yeah, so, and this thing hopefully is clear. Okay, so I hope that you find this session helpful, and please send more questions to the Hangout that we have, and talk to you later.